Now, we need to stop a little bit because we need to talk about some results which are crucial in the theory of being more generally crucial in finite element theory. However, they were developed by Weierstrass in a moment, in an historical moment again, when computers were not even conceived and conceivable. So I want to tell you a result which is very easy. You find it in a book very popular, for instance, Kolmogorov. It is one of those beautiful books of me. I know that you don't like very much Russians, but Russians books were very good, very cheap, very well written, translated in every language. So this Kolmogorov was written even in Italian. But you find the theorem of Weierstrass, you find everywhere. It is very instructive, I think. Consider a continuous function defined in a given interval. Okay? Then consider this function plus epsilon. And then consider this function minus epsilon. So if you have f of x, you can define f of x plus epsilon and f of x minus epsilon. Then you have a stripe. Okay. By the way, this reasoning has been done again by Lagrange. Okay. If you have a function g of x such that gx minus fx absolute value superior when x belongs to this interval less than epsilon. So if the biggest value of this difference is less than epsilon, what you have? You have that the graph of this function g is inside this stripe. So, in a sense, you have that g of x is epsilon distant from f. Okay? You know how we call this number Lagrange norm of this difference. Now, why we are interested in this concept? Distance between two functions. There are several reasons. First, when you measure something, you never get an exact result. So, consider a beam. You clamp it, you apply some loads. how much is this applied load? You measure it, but you have an error. Then you have the deformation of this beam. You go there, you measure the shape of the beam. Of course, when you measure the shape, you get an error. So what happens is that you need a theory which tells you if I have a force applied, and this force is F plus or minus epsilon, the shape of the beam will be this shape plus or minus delta. Well, epsilon and delta are two small quantities to be suitably chosen. Nobody can measure exactly something. I don't know what you have done, but when I started my studies in physics, I think the second week we went in the lab and they said us, measure this. They gave us an instrument which was very sensitive, and there was a wind in the room. The change of temperature in the room was changing the result of the measurement. So we couldn't say which was the measure because it was changing continuously. So we needed to declare that the result of a measure was an average plus or minus a variance. I don't know why engineers, when they plot the result of measurement, use a point, which is meaningless. You must consider crosses. Every measure has a result which is an interval, an average, and a variance. Okay? So it is clear that in order to have a predictive theory, in the sense we have said in the previous lectures, you need to introduce the concept of distance between functions. Okay? So this is a first reason for which Lagrange needed strongly this distance. But there is also another reason. You told me that you know that square root of 2 is not a rational. So, if you have not seen the demonstration of this, I strongly advise you to go and read it immediately. I have discovered that my past PhD student, who now is a big professor in the United States, who has many thousand citations, didn't know that square root of 2 was not a rational. Which was taught in Italy until a few years ago at the second class in high school. My mother didn't manage to understand why square root of 2 was not rational, and for this reason had a lot of troubles. This was considered a pillar of Western civilization. To understand that the rationals are not enough for covering the set of all numbers. Okay? How we handle this? So, you have a practical problem. This is 1, and this is log square root of 2. So, you are the owner of a piece of land which is a triangle. This is long 1, this is long 1, this is long square root of 2. So you have a practical problem. You must buy enough pieces of wood for building a fence here. This is a practical problem. So you need to estimate square root of 2. There is a procedure which allows you to find a sequence of rational numbers which is becoming closer and closer to square root of 2. Using Cauchy nomenclature, you have a sequence of rational numbers which is converging towards square root of 2. So, if your error is 3 millimeters in building this fence, in the sense that if your number is plus or minus 3 millimeters, you can stop in building the converging sequence to square root of 2 when the error is less than 3 millimeters. Why I said 3 millimeters? Depends. If you are a goldsmith, then for building a jewel you will need 1/10 of millimeter. So epsilon depends. If you are a dentist, you know, my dentist caused me a lot of troubles. It was wrong 1/10 of millimeter. And he placed in my bone a wrong rivet, which was located 1/10 of millimeter in the wrong position, and I felt pain for months. So, epsilon depends. You cannot tell that 1/10 of millimeter is nothing. In your bone, at the place of food, it is a lot. So we cannot tell you epsilon, how much it is practically. You need the abstract concept of being close of a small arbitrary quantity. This is not something for mathematicians. This is something for engineers, physicists. This is practical. Okay? So, in order to do the simplest calculation, how to measure the perimeter of a piece of land, you need to understand the concept of converging sequence of rational numbers. So, whenever you need to calculate numbers for forecasting the behavior of an engineering device, structure, artifact, you always need to solve the following problem. I have a theory. This theory is forecasting something. I need to calculate an approximation, suitable approximation, an approximation suitably precise of the forecasting given by my theory. It is not necessary to find the exact solution. In a sense, it is completely useless to find the exact solution, because nobody is measuring exactly something. So you need to know a reasonable approximation of your solution. When you use a computer, you get an output. Sometimes it is some spots on a screen, colors on a screen. You have a pixel. It is useless to go ahead and calculate more and more. When the resolution of your screen is reached, you don't waste your time in continuing doing calculations. Okay, so once you know epsilon, which is acceptable in your context, either you use F or you use G, it is the same. They are equivalent to your aims. Okay? You have to learn these things very well. Not only we should keep in transmitting these informations to the students. Now I'm telling you, I'm repeating a lecture which I heard when I was 19, and I want to tell you who was the professor who was teaching me these things. He was Ettore Pancini. He got a nomination for a Nobel Prize, but he never got it because he was communist and Italian. And Italians did not promote him because he was communist. And Russians did not promote him because he was Italian. Okay? He was the discoverer of cosmic rays. The person who, with other two colleagues, discovered cosmic rays. And he came to us and he gave exactly this talk. So I hope that you will be able to give this talk in 20 years to somebody else. So the tradition will go ahead. Which are the most beautiful, well-behaving functions defined in an interval? Polynomials. Why? Because you can calculate the final result of a polynomial doing sums and products. So, the simplest functions you can conceive are polynomials. You can calculate the value of a polynomial easily. Okay? Now, do you know which problem was conceived by various in a given moment? Given a continuous function f and given an epsilon, can I find a polynomial which is close to f less than epsilon? This is the problem of approximating polynomials of a given continuous function. Okay? The answer is, for every epsilon, there exists a polynomial, at least one. There are many polynomials. There exists at least one polynomial which is close to your continuous function. Epsilon close to your continuous function. This theorem is fundamental in computer science and in numerical analysis, because it means that whatever function, continuous function you have, which is the solution of your problem, whichever is your problem, you can find always a polynomial which is close to this function. Now, the bad news, this is the good news. The bad news is that the theorem of Weierstrass is not constructive. So, it tells you, this is typical of mathematicians. It proves there exists such a polynomial, but it is not giving you the instructions for building it. So now you can understand why Taylor was so popular. Because he was telling you how to build a polynomial which is approximating a function. But Taylor, the series is very bad. You need a lot of derivatives. While the theorem of Weierstrass is true for every continuous function. Okay? Now, I don't want to go too far in this discussion, but I think that we can conclude this discussion with this remark. It is a little bit as if polynomials were the corresponding of rationals in real numbers. For every real number, you find a sequence of rationals which are converging to the real number. For every continuous function, you have a sequence of polynomials which is going close to the given continuous function. Okay? The man was understood in deep detail. This was a Russian scientist whose name was Sobolev. But I don't want to be too nationalistic, but in Napoli we had Cacciopoli, who was very close to his results, and he proved a lot of theorems in this direction. Okay. Why talking about this? Yesterday we wrote an energy. Okay? And we said, in order to solve the problem of Galileo, the problem of finding the shape of a beam under externally applied loads, we need to find the minima, so the functions, which are minimizing this energy. Okay? What we did, following Lagrange and Euler, we estimated the first variation of this quantity. We assumed that this first variation is 0. Then, what we needed to do? We needed to accept that this u is 4 times differentiable, and we found a necessary conditions, some necessary conditions for this equation. So we said that if delta epsilon t equals 0, this implies that km u second 7 plus b equal 0, which is the Euler differential equation. This is the equation of elastica. Euler wrote in Latin, so in English now they still use the Latin word elastica. It is the elastic curve in Latin. Okay? Then you have boundary conditions. Either you impose mathematical boundary conditions or you deduce, starting from this equality, these suitable boundary conditions. Okay? Good. But for doing this process, you need 4 derivatives. So it could be that one minimum of these is not 4 times differential. This energy requires the existence of 2 derivatives. You can express this energy simply if U has 2 derivatives. You are not obliged to consider a situation where you have 4 derivatives. Okay? Now, don't believe that practical problems are friendly. You know, phenomena are phenomena. They don't ask you the permission to be complex. So it happens very often that a logical possibility becomes a painful reality. Okay? So, useless assumptions should be avoided. One should try to avoid to develop a theory with useless assumptions. Now, do you know why this equation is very famous? Because using these equations, engineers could build very complicated structures. If you go to New York, you find the Statue of Liberty, and in the basement of Statue of Liberty, you find walls covered with calculations. The engineer who designed the Statue of Liberty was Eiffel, the same old tower in Paris. And he not only gifted with his friends to the United States the Statue of Liberty, but he gifted also all calculations he has done for designing it. Okay? He wanted to prove that French science was better. There is always propaganda behind this. And he could design complex structures applying these equations for every beam constituting the structure, which is painful, and usually engineers were trained in learning good tricks you can find for solving by hands these equations. Doing calculations on a piece of paper. So this necessary condition has been used for designing structures. By the way, the Tupolev airplane has been designed by Tupolev, assuming that the wing is a beam, an elastic beam like this, and also the, I don't know how to say it, the tube where you have passengers is another beam. So it's a system of 3 beams linked, clamped one with the other, and he wrote these equations in a very clever way. Okay? However, we want more and more. We want to design structures very complicated. And there are limits to our capability of doing calculations with piece of paper and pens. So we wanted to use computers. Now, the idea is the following. Of course, this is a very simple example. I thank you for giving an idea. Then we will repeat these reasonings in a more general setting. So what you can do? You can take the interval 0 and This is could seem the brutal way of solving this problem. It is rather brutal, but it is very effective. Then you can find a reasonably refined partition of this interval. So you choose x1, x2, xi. The last xn is equal to n. Okay? How you are placing these points in this interval, it depends on your problem. You can place them, this is a mesh, you can place them with the same distance, uniformly in the interval. You can gather, if you expect that something is happening in a point, you can have more of them in this neighborhood. This is your understanding of the problem, which gives you this solution. Then you remember the theorem of Variational. In every interval here, I have the solution u. However, I can approximate it with a polynomial. So you can choose in every interval. So in the interval xi plus 1, you can choose a polynomial. You can have a Lagrange polynomial, you can have what you want. It depends on your problem, you will choose a clever polynomial. So you have a polynomial pi of x. This interval and the polynomial you have defined on it is a finite element. What we could call finite element. Of course, you cannot choose these polynomials as you like. At least you must get a continuous function. Or you can decide I want a function which is continuous together with its derivatives up to the kth order. It is wise in this context if you check what happens to the second derivative. Okay? So you choose a set of polynomials, and in order to draw it, let us choose piecewise linear elements for u second. So you assume that the approximation of u second, let's call u second theta, is given by a piecewise linear, but this is only for telling something. Okay? Why I want to give you an example? Because I want to underline that these polynomials have some free coefficients. If you have chosen for the, of course, if your approximation has a second derivative which is piecewise linear, then you can integrate 2 times, so you get a cubic, piecewise cubic function for u. Okay? Some of these coefficients you need to fix in order to get continuity of the function and of the derivatives. some of these parameters, you have free hands in choosing them. Okay? We can call these parameters degrees of freedom if you want. So, what you have? You have a number A1, A2, A capital K. You have a given choice of real numbers. When you have blocked these real numbers, you have specified all the polynomials, so you have a tentative solution for your problem. Okay? I want to be clear. If you are not careful in understanding all details of this story, you can behave as the famous, my past PhD student, who believes that every differential equation has as solution a polynomial. So I discovered that he didn't know what is square root of 2, because he said, what you are telling? So if I write x squared equal to 2, the solution is a rational. So try to understand the complex structure of mathematical objects we are working with. If you try to solve this exactly with a rational, you will never find a solution. However, with rationals, you can go as close as you want to the solution. So in general, if you have a differential equation, you could have a solution which is not a polynomial. However, you can approximate, at least piecewise, this solution with polynomials, which are very good for doing calculations. Okay? So, I have these parameters. If you have piecewise approximation of u second, piecewise linear approximation for u second, these parameters correspond to the value of u second in these nodes. So, these values you can choose as well. Okay? When you have chosen A1, A2, AK, you have a tentative solution, a candidate approximation of your solution. So you have u tilde, which is a function of x, of A1, A2, AK. Okay? This function you have built in such a way that you can calculate its first and second derivative. So you calculate these derivatives, and what you do, you take this and pop. You calculate the integral you want to minimize. We have done a wonderful trick. By the way, this trick is based on some beautiful theorems of Banach. Okay? You take this, you place there, and epsilon t now becomes a function of k real variables. So let's call it another way. epsilon t tilde is a function of a1, a2, ak, which is an animal you can study more easily. So, let us repeat slowly, because these are fundamental ideas. I know people who are like, this morning I woke up a little bit polemical. You should know that there is an ape. It is a kind of, they call it small chimpanzee. Okay, this ape is, as a name, his name is Kanzi. Using a computer, Kanzi can talk with humans, answering questions, invented new words. For instance, he pushed ice and cream and he meant ice cream. He invented this. Okay? Kanzi is very good with Pac-Man video game. A body can believe that he understands the mathematics behind Pac-Man game. Okay? So please, don't believe that you can play the video game of a program without understanding what is behind it. Behind console, behind Nastran, behind everything, there is a strategy of approximation which is based on Banach and Sobolev theorems. Okay? And you must understand what is behind. Otherwise you are a kind of Kanzi playing with a video game without knowing what he's doing. Okay? So, we have a functional, so we have a rule which, given a function, gives you as an output a number. Okay? So, the domain of a functional is a set of functions. I know it is difficult. By the way, the map is a function. So I could say that the energy is a function whose domain is a set of functions. But in order to avoid this bad sound and this dangerous repetition, we decided to call functional a function whose domain is a set of functions. Okay? What is an integration scheme for finding the minimum of a given functional? It is a clever trick which replaces the functional with a function. So instead of having a rule which for every shape u of s gives you back a number, the deformation energy, you have here a rule that to every A1, A2, AK gives you back the deformation energy. So this is a kind of simplification of your problem. For transforming a non-computable problem in a computable problem. Of course, if you have chosen your utility in a completely wrong way, you are not approximating anything. You must be very clever in choosing this approximating strategy. This is clear. Okay? So if you close your intellectual eyes and you click in the console windows Lagrange polynomial sixth order without knowing what you are doing, most likely, you know, nobody kills anybody with blind eyes and with a gun. You shoot without knowing what you are doing. And it is very unlikely that you kill somebody. And if you kill somebody, you don't kill your enemy, for sure. Okay? So, you must understand what you are doing, what you are approximating, why you are choosing this approximation, what you are expecting will be the result. Okay? Another of my PhD students, he believes to be a great expert in numerical analysis because he likes very much installing software, using Mathematica and these kind of things. Okay? However, when we have joint works, he couldn't understand what was happening, and he came to me to discuss what he was doing. One day he decided that I was a useless scenario person, and he decided to write the papers by himself. Since then, he has published very few papers. He is clever, but he never wanted to understand what is behind. So, you must understand that numerical analysis is a strategic art. And you need a lot of mathematical knowledge for handling correctly numerical analysis. What you are doing now, calculating partial derivatives, for instance. So, if you can do it, you calculate this derivative, you equate this to 0, and you have an equation, in general with more than one solution, thanks of which you find these numbers. Then you can have Newton's strategy for finding this solution. You can use many techniques, but these are much simpler and very well known because you have reduced the problem of finding the minimum of a functional to the problem of finding the minimum of a function. Okay. Now, how many cases do you need? Depends on the problem. How you construct U tilde starting from the A's? It depends on the problem. So every problem will need the development of its own strategy. But the general scheme of solution is this one. Now, why this is better than the integration by part I've shown you? This allows you to approximate solutions in which only the second derivative exists. So you don't need very regular functions. Functions who are uselessly too regular. So in this way you catch much more. You can find even bad solution, not so good, in an approximate way. Okay, I think that before having a coffee, I must tell you that the most creative mathematicians now in the world are studying energies. So what they are doing? They look for properties for energies which are assuring you that the solution is unique or there are more than one solutions. So, in a sense, creating a mathematical model means finding the right energy. Give me an energy and I describe your system. This is the idea. Huh? So somebody will tell you how you know the energy. You can answer like Popper, the famous philosopher of science. I got a vision. Okay? I don't need to explain to you why I have conceived this energy. I will explain to you what I am forecasting with this energy. If this energy is forecasting phenomena, then it is good. Okay? I want to look for the conclusion of Piola of his book, because it is beautiful. So I will read this. Okay, so let's go to a lot. I want to tell you this. We try to concentrate the lectures in the morning. Okay? So you will be allowed to go to Rome. You must go to, not you are ordered to go to Rome. Okay? You cannot stay here and not visit Rome. It's crazy.